Thanks, Mugund. And thanks to Sasha and the other organizers for inviting me to give a talk at this really nice conference. It's been great to hear. I mean, just to clarify, I am not an organizer for the conference, so I meant what I just said. This was not a joke. Okay, so thank you. It's been a great time here at KITP. Really nice conference week too. And so, yeah, I think by the titles of the talks, you can tell we're all coming out of a pandemic. Yeah, so I'll be talking about the scale separation problem, which has been one of the dominant themes of the conference in a way, which makes me happy because I think it's an important problem. And we've talked a bit already in some of the talks in the past couple of days about why it's an important problem. Here I've just listed a few different points of view from which it seems important to me. I'd like to understand the swampland better, the space of large N CFTs. We can view the presence of extra dimensions as a proxy for string theory. And so in this sense, these solutions can help us probe ideas about string universality. They're also a step toward constructing cosmological solutions that approximate the real world. And finally, they include the pure gravity problem and, in a sense, generalize it. There's been a healthy appetite for the conformal bootstrap at large N to solve this problem. Deservedly so, I think, given the other accomplishments of the conformal bootstrap. But I think to do so, we need to ask the right questions, and that's partly what this talk's about. So I certainly won't solve the problem, but I'd like to reframe it in a way that I think will help us solve it. So the rest of the talk will proceed as follows. First, I'll just give a brief self-contained introduction to the problem, which we've already heard some about, so I won't belabor it. And then I'll turn mostly to the CFT and try to say what is the dual problem and how we should solve it. The last part will be a slightly different question, addressing the idea that there might be pure gravity theories in higher dimensions and trying to bound the degree of scale separation that is possible. So the punchline of these two parts of the talk is the following. The scale separation problem in ADS is a subleading retrotrajectory problem in planar CFT. And I'll derive an upper bound on the prospects of pure supergravity in ADS5 by studying 40 n equals 2 SCFTs, leaning heavily on the work of others. And here's the bound. So it's a spectral bound on the dimension of the lightest primary with a certain type of quantum number. And here's the bound. There must be an operator of delta less than delta star, which in general is bounded above by root C times some correction factor at infinite C. Okay. So, oh, sorry, thanks. Euler gamma. Yeah. Thank you. Okay. So the ADS scale separation problem, in short, is the question of whether large extra dimensions are required in the Einstein gravity regime when we construct theories that look like the theories we like with large N and a large gap, in a sense to be made precise. Do we need lots of extra light stuff? That's the CFT caricature of the problem. So the sphere, or whatever this compact manifold is drawn as smaller than the ADS. And so we can recast this in the following way. The Hamskirk-Penedonis-Polchinski-Sully paper that codified what it means to be a holographic CFT in terms of bootstrap data tells us that there's some local ADS bulk given some conditions on the boundary theory, but it leaves open the question of in what dimensions the bulk theory is local. So that's the question of how much light stuff you have and whether the extra dimensions are large or small. And in this talk, large means ADS sized. So as we know, familiar string vacua have large extra dimensions. In other words, the supergravity approximation holds in some dimension capital D, which is greater than little d plus 1, where the CFT lives in little d dimensions. And, well, it is clear why this is harder to do, right? If you start from some, say, 10-dimensional string theory setup where the vacuum is flat space, then you need to use the string fields to compactify things, and you have to work harder to compactify them more. And so this is really a bona fide string theory or M theory problem, because the smallness of the extra dimensions means that, broadly speaking, you'll have some string or Planck scale curvatures in the problem. So this is not a well-defined notion purely in the context of supergravity. Now, there are lots of candidate solutions. I've listed the authors of some here. LVS are not the authors' names. Unfortunately for them, that's come to label their solution, but that was a solution by Balasubramanian et al. And as we heard a bit yesterday, the candidate solutions are hard to ratify absolutely because quantum gravity is hard. And that's why people want the bootstrap to solve this problem, because like other problems in quantum gravity, there are, we can use the foundations of local quantum or conformal field theory to translate thorny questions and then hopefully answer them. Okay. Now, I'd like to just point out that there are two versions of the scale separation problem. One is the sort of stringy version, and one's the M theory version. So in the stringy version, we think of the extra dimensions as being at the string scale, which is parametrically lower than the Planck scale, while in the M theory version, they're at the Planck scale. This puzzle exists even with maximal SUSY, as we heard a bit during Shai's talk. So we're taught that local R symmetry is always geometrized in ADS, but is this really true? Let's consider the space of 4D n equals 4 as CFTs. It's an open question as to whether n equals 4 super Yang-Mills is the unique such theory. And at large n, there's a version of this, which is the scale separation problem. Do there exist, say, pure ADS5 solutions without the S5 factor in a consistent theory of quantum gravity? There are intermediate possibilities, but that's the one that is the most natural. Now, this is still an open question. There have been some proposals in the literature recently with different points of view, as indicated by the placement of these references on this slide. So we've got Team Sphere over here and Team ADS over here. But we don't know the answer yet. And just to put this in the framework of what I said before, the putative exotic n equals 4 SCFT that we're talking about has no weakly coupled region, else it would be super Yang-Mills. So G string is order 1, or at least finite, and this is an M theory version of scale separation that we're seeking. Question?
What do you mean by geometrized? Would you allow canceling central charge of the string by, say, some CFT, which does not have a geometric interpretation, but introduces nice stuff? Is that part of what you're saying?
It's not strictly part of what I'm saying. No, I think, yeah, I think from the CFT point of view, we should put those two in the same bag, and it would be nice to know whether you can. It'd be nice to formulate the problem in a way that can address non-geometric solutions in the bulk.
The pure ADS part, you mean a large pure ADS part with the small position?
Yep, and then the rest of the dimensions are compactified somehow, the Planck scale. Yeah. So the main consequence of this, for the spectrum is that you don't have all these like KK modes, right? So that's where we're going. Yeah.
So those like not in the top of region, but the equals for have a scalar, right? The gravity.
Yes.
Well, I guess your point is that it might not.
Yeah, you can't take it to zero. You can't take the exactly marginal coupling to zero in such a theory. Something must cut that off. There is a exactly marginal coupling, but it must get cut off before you can go to weak coupling. Is there a question behind? Yeah.
So if the arithmetic is not coming from icon to we have a sense of where it could come from if you have
Not exactly, no. But that's my motivation, to rephrase the problem in better language to try to answer it. But I think, yeah, that's.
Is there any example of anything like that?
I'd say no. I mean, in the framework that I'm talking about here, in the ADS CFT context, no, there are no no examples in which a local R symmetry is not geometrized. For CFTs that have, this holographic Einstein regime, just to be clear. Yeah, everything's different in flat space, that's for sure, because you have toroidal compactifications. The key is that the ADS has the negative curvature, so we need to balance this. So I feel the game changes when you change that. We can shrink tori and so on. Yep.
The scale separation issue in terms of the gauge coupling of the R symmetry gauge field, because the R symmetry gauge field, my gauge field. Can you say what conditions scale separation is in terms of
I don't, let's see. I don't want to do that because I don't feel, I don't feel like I can, yeah.
Pointed out by, for instance, I have a paper that scale separation becomes, no scale separation becomes seen as linearly correlated for the R symmetry.
I don't think that helps us solve the problem, phrased that way, because you want the logic to be a little inverted, but yeah. Okay. Great. So now some conceptual comments. This is a semi-classical question. At finite Newton's constant, there's no parametric scale with respect to something can be large or small. We don't even know how to measure distance in that theory. We don't know what the word scale would mean. So to me, without parametrics, the question ceases to be sharply defined. In a CFT language, we can study conformal bootstrap at large but finite n. But at finite n, there's no privileged scale in delta space. There's not really a real distinction between something that's a large KK mode or a small excitation. We can certainly do the bootstrap, and we do. But I would say there's nothing genuinely gravitational about such extremal theories. But I think there's a different issue, which is related, which is that when we look at plots like this that we get from the conformal bootstrap, where we have plotted, say, 1 over the inverse central charge on the x, and some observable, like a conformal weight on the y-axis, and there's some allowed region and some extremal curve. There's a few comments I want to make about this. The first is that, in accordance with what I just said, the pure gravity region is out here, right? The semi-classical pure gravity region, where that term really has teeth, is out there. And this line is not a theory. And I don't mean that in the sense that you solve a partial bootstrap problem and you need to try to incorporate all the constraints, and you're not sure if all the constraints really get at the answer, and you need to optimize your numerics. I don't mean in that sense. I mean, it's just not a theory no matter how hard you try. And the reason is that the central charge can't depend on continuous parameters. This is a discrete space of theories. If I want to move this way, then I need to jump. So this is at best an interpolation between theories. So, as I said, why is this? Well, because the central charge, think of this as A in 4D, or A or C in a 4D SCFT, or C in a 2D CFT. It can't depend on continuous parameters like exactly marginal couplings. So we can't reach this regime by tuning some parameter of some theory and going out there, or vice versa. We can't do something to our gravity theory to move down to finite C. There's a sequence of theories that takes us out to large C, and perhaps to whatever gravity theory we're studying. So we need to pick some curve or sequence in this space of theories, but which one? This is not a meaningful question from the abstract bootstrap point of view. You need to move outside of the space of CFTs to connect these theories. So if there's a theory out at large C that you're trying to get to, you need some principle or some explicit construction, if you get lucky, like a Lagrangian, to make this curve for you to go out to large C. And so a lesson from this discussion is that we should ask questions that at large n single out the pure gravity theory that we might be trying to study. And that's what I'll try to do. So now we'll move to the CFT. And so in the CFT, there's been some work about trying to understand the ADS scale separation question. It's not the same as the spectral gap question. It's really a statement about the distribution of dimensions in some intermediate regime. You can have 1 or 2 or 3 light scalars and then some gigantic gap, and this is indeed a property of these DG-KT solutions, so it was discussed yesterday. So it's not about the spectral gap, it's about the distribution. It's a bit more refined. And in this paper with Fernando Alday from a few years ago, we formulated a one-loop sum rule, in other words, a first non-planar correction sum rule that bounds the number of both dimensions, but we don't know the bootstrap principle to impose that tells us that you either can or can't have scale separation. So we're looking for something else. So a few points in succession. I'd like us to think of this as a spin 2 problem. In particular, symmetric and traceless spin 2 problem. These operators are the smoking gun of large extra dimensions. We're looking at theories that have a supergravity approximation in some dimension. And so this type of operator must descend from the d-dimensional graviton. This is unlike scalars, vectors, tensor moduli. Symmetric traceless spin 2 are special. So some intuition from the bulk is that if we define n2 as the number of light spin 2s, light meaning dimensions order 1, mass is order 1 in ADS units in the bulk, then if we had d equals d plus 1, then there would just be the graviton. Okay. So if there are more than one light spin 2 field, in other words, if there are some massive spin 2s, then capital D is greater than d plus 1. From the supergravity point of view, it's natural to expect that actually n2 is infinity. And there's been some nice papers along these lines, and Alessandro talked a bit about this issue yesterday. For example, these authors argued that the symmetric traceless spin 2 spectrum should start at some order 1 value based on some diameter bounds motivated by looking at positively curved closed Einstein manifolds. And that's a nice setting to get intuition here because geometric compactifications, in supergravity often employ this type of manifold. And these authors here proved that for closed Einstein manifolds with no boundary and positive curvature, the ratio of successive eigenvalues is some order 1 number. Basically, it's 4. Here's some plot from their paper. This is at 4. There's some slight dependence on some other eigenvalue of some other Laplacian, but yeah, the point is that if it starts at order 1, then there's an entire tower of order 1 operators. Okay. So this is, yeah.
Alessandro was saying that there was a counterexample to this.
No, but I think so the first operator was extremely light, but the others were still order 1. So this is fine. I mean, but also I don't think they strictly fall in this classification, so everything holds together, but yeah.
It was light in ADS units.
Yep.
And the others are order 1 units. Okay.
Mm-hmm. Okay. Yes, some supergravity in some dimension. Yeah. Yep.
So you want to have some equal operators, or else you want to not just know higher speed path, right?
Yes, I'm looking at theories that obey that kind of condition. And indeed, that helps me transition to the next slide. So we're going to consider sequences of local CFTs with an asymptotic limit of large n and an independent scale delta gap, which is the gap to the first single trace higher spin operator. Okay. So in other words, we're looking now at the stringy version of scale separation. Okay. This is the bulk EFT expansion around classical Einstein gravity. There have been some nice works making more concrete sense of this recently. So there are some beliefs in the air about what might be true of such theories. First one is that there must be some infinite tower of such operators with dimensions order 1. This is the sort of no scale separation idea. If there exists one non-conserved spin 2 with order 1, there must be an infinite number. And finally, you might believe that there are no consistent truncations in ADS with a finite number of spin 2s, which is slightly different because it invokes the OP coefficients in making that statement. Okay. Okay, so we're now seeking a purely classical criterion, and I want to emphasize that we should only use conformal symmetry, not global symmetry. Although, in general, there will be lots of massive spin-2 singlets under whatever global symmetry. So, okay. But now let's get to the point of what I'm trying to introduce, which is that this is a Regge problem. Because in a planar CFT, the Regge intercept is bounded above by 2 for the leading trajectory, and therefore also for all subleading trajectories. And so that means that spin-2 and higher operators must live on such trajectories. So there's a general story in non-perturbative CFT about such families of operators. In the context of planar CFT, I want to think about the single trace trajectories. You should think of the local operators as living at integer spins, and the trajectory analytically continues these away to complex spins. That's the foundation of the construction of light ray operators, but we won't need that level of sophistication. And so the CFT dual of the ADS scale separation is now how sparse can the single trace spin-2 trajectories be? And I think this is useful because Regge trajectories are rigid objects that tie infinite towers of higher spins together. Let me say a little more about these. Let me review just the formula for the leading trajectory. Okay, so this J of nu, I should have explained, right? So I nu is defined as delta minus d over 2. This is some function J of nu. You slide along the trajectory by changing nu. Okay, so for the leading trajectory, it takes this form at large gap. Okay, this can be derived by demanding the existence of the large gap limit plus some property of asymptotic linearity of these trajectories at large nu. So the upstairs is just a polynomial. It satisfies the two conditions that when you set spin 2, you get the stress tensor, and it has dimension exactly d from the 0 here. And when you set spin 4, you get delta equals delta gap, which is the definition of delta gap. Okay. So my claim is that the same arguments apply to subleading trajectories. I think this is a very uncontroversial claim. The arguments are very general. So the subleading trajectories, which are labeled by some n, which takes values 2, 3, etc., has the form of some leading constant, capital Jn, minus some function of nu over delta gap squared, plus dot, 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 where I should have said here and here, this means 1 over delta gap to the 4th, and so on. Okay. This function must be even in nu. This is so-called shadow symmetry. And at large nu, it must go like nu squared. Now, the spin Jn is the spin of the only light particle on this trajectory, whose mass is, or conformal dimension, is found by solving f equals 0. Nu n must not have a real part, that's unitarity. And then you read off the dimension of this operator, okay? So if there exist n2 light spin 2 particles, then there must exist n2 spin 2 trajectories, where spin 2 trajectory means the intercept is 2 at infinite gap. To envision these, it's useful to make what's called the polynomial approximation. I think this actually might be an exact statement, but I'm trying to be conservative and don't 100% understand whether we can always take this approximation. But in any case, right, the dimension of the dual operator is d over 2 plus some constant b2n. And so these trajectories are just translates of the leading one. We're just shifting them down by some constant proportional to the mass of the bulk particle. So here's a picture. We have a bunch of trajectories that pile up at spin 2 in the case of no scale separation. There's a bunch of light spin 2s out here, moving on out. The trajectories pile up near 2 with order 1 over delta gap splittings, 1 over delta gap squared splittings, I should say. And so we can refine this slightly further. This is really a Regge intercept problem. You can focus on the intercept because it encodes the fact that, it encodes the mass. And so, but better said, if there are lots of spin 2 trajectories, then they all have intercept near 2. So we can just talk about the intercepts if we want to. The rest of this functional form is fixed by the demanding the existence of this large gap limit. So finally, having reduced this as much as I can, the question is, can a planar CFT have a finite number of spin 2 trajectories or spin 2 intercepts? That is a necessary condition for scale separation in the bulk.
Yeah. So with or without
Those zeros are statements about correlation functions, right? C delta J. So here I'm just looking at the spectrum itself. So I mean, that means that you might not be able to detect them all in some correlator.
The trajectories at the second two doesn't mean that the number of vectors. There could be more trajectories than the one that are required by the classes.
Is it really possible that you could have a trajectory? Sorry. So maybe I'm making some kind of assumption that there is some correlation function in which these things would appear. I'm imagining something. Sorry, I mean, but these operators that don't appear in those correlators, they are in the theory. I mean, we wouldn't say they're. Sorry, you're talking about these right, the trajectories that cut off. Yeah, sure. I think I'm.
I think it's possible to have a scenario where you just have one black dot and you still have a lot of trajectories.
I don't. Is this really compatible with the large gap limit in the planar theory? Okay, sure. Thanks. I'm not sure about that. So the idea is that we can now use the rigid structure of these planar trajectories, and we can also, if we want, focus solely on the intercepts. So if a finite number of such trajectories is not possible, then the scale separation is ruled out. As an example of how this is useful, we can also think of this as a statement about the higher spin spectrum, right? We don't have to think about the spin 2 part. We can think about the fact that these spins are all tied together. And you can prove the following statement. If the spin 4 dimension on the nth trajectory is equal to delta gap times 1 plus order delta gap to the 0, then it must sit on the spin 2 trajectory. Basically, because if Jn were, say, 1 or 0, then nu, this parameter, has to make up more to jump up to 4. And this would acquire a coefficient like 2 or root 2 or something. So we can then say again, scale separation is a statement about large splittings amongst the higher spin operators. So must there always be some large approximate higher spin degeneracy in this massive higher spin phase? I don't know. If so, then scale separation is ruled out. Okay. So finally, I'm going to move to the part of this pure gravity bound in this other setting. So this question is now slightly different. We're going to suppose scale separation is possible. How high can we push up the lightest state? This is the typical pure gravity large N bootstrap question. To guide our thinking, let's be more precise about black hole thresholds in higher dimensional ADS. There's a parametric separation between small and large black holes in ADS-D greater than 3, because the central charge scales with m Planck to a power greater than 1. So large black hole microstates have dimensions of order c or above, but small black hole microstates, which we should think of as having Planckian masses, appear at some fractional power of c. Okay. So this is a little different from the ADS-3 case, as we'll return to later. Now recall, as we discussed, that even in CFTs and even in their BPS sectors, the scale separation question, the possible gaps is open. I'll focus on 4D n equals 2 CFTs, where this is the R symmetry algebra, SU2 times U1. Of course, we want to focus on SCFTs for parametric control. That's part of the reason. Now, in this context, these theories are labeled by the rank R of the Coulomb branch. This is a good bootstrap quantity in the sense that R is just the number of a certain type of protected multiplet, a quantity that can be defined abstractly, independent of Lagrangian or whatever other considerations. We're going to bound the scalar gap in the sector of R-charged chiral primaries. So these have vanishing SU2 charge. Their dimension is equal to their U1 R charge. And we're going to look at scalars, right? So the primaries are scalars in this case. Now there's no prior from black holes because there are no BPS black holes with scalar spin. So I don't quite know at the beginning what we're supposed to get, or even if we are supposed to get a bound. But we get a bound, and it follows from putting together hard work done by other people, a lot of work over the years by Martone and Argyris, and then at the same time as this one, a paper by Corsi and Cicciotti. And it follows from two fundamental facts. The first is that the central charges are fixed by this Coulomb branch data, and in particular their operator dimensions. There are exact formulas for A and C in terms of this data, but I've written it in terms of 2A minus C, where all that appears is the sum of the dimensions of these operators. There are R of them, so sum from 1 to R. And here's the Hoffman-Maldacena bound for 4D n equals 2 theories. There are exact formulas for A and C independently, but all I'll need is this. Ultimately, I'm interested in taking A equal to C at large C. Notice that for any A over C greater than 1/2 at large C anyway, large C requires large R and vice versa. This is an interesting consequence of this formula. This originally appeared in work by Shapiro and Tachikawa. One of the points of the more recent work by Martone is that it applies independent of the assumptions they made. And indeed, A and C have independent formula for the central charges. Okay, so we can apply this fully generally with some small but widely held assumption here. So the central charges are fixed by this data, and the dimensions, lo and behold, are bounded. They're not just bounded, they actually have to belong to a privileged set of rationals, which obey some beautiful number theoretic constraints. The maximum dimension is the maximum value of n, such that this totient function is bounded above by 2 times the rank. So now the game is simple. We're interested in the case where A is approximately equal to C at large C and large rank, therefore. Take A equal to C, maximize all the dimensions, and invert it to write it in terms of C. And what do you get? You get this bound. More generally, if you there are equalities here. So if you take the sum of dimensions to scale like R to the 1 plus Z, then the gap decreases correspondingly, goes like C to the Z over 1 plus Z, where Z is between 0 and 1. In the case Z equals 1, there are log corrections. That's what this is. Okay. So some comments. The lightest tower of these states cannot be pushed up to the large black hole threshold of order C. That's the first, I think, most obvious thing. This applies to both string and M-theoretic theories. There doesn't need to be a delta gap in the game. And I should also point out that we have not made use of all the constraints. Right? I haven't used the rationality. I haven't used various more sophisticated number theoretic constraints on the allowed R tuples of dimensions. Turns out you can't actually just select R dimensions from this list. There are constraints on the tuples. It's an interesting open problem to study these at large R, which I hope to get Mario and friends interested in. And you could also insist on there being a finite flavor group at large central charge. I haven't done that either. But without doing all that, you still get this nice bound. We're heading toward the end, so let me just put this in some context. There'll be a couple more slides, and then I'm done. Obviously, we should make an analogy to ADS3 CFT2, where we've all thought about the pure gravity problem in one form or another. The best current modular bootstrap round in 2D at large central charge is this, of these authors. In this context, there's no parametric separation between small and large black holes because the Planck scale is proportional to C. The small black hole threshold is defined as where the horizon gets Planckian, the entropy becomes order 1 and looks like it's starting to go to 0. Let's define the large threshold as where BTZ or Cardy universality sets in, which thanks to the works of Hartman, Keller, and Stoika is C over 6. From this thermodynamic definition, you see that this bound is somewhere in between. If you use the horizon size instead to define large, then large is actually very close to here, right? The radius of the black hole is ADS sized even when you're just some finite amount above C over 12, finite times C. But let's use this sort of, more generous definition of large. This bound is somewhere in between small and large. And that's what we found in this 4D n equals 2 context, right? Delta star goes like root C times corrections, which is between C and C to the 1/3, which is M Planck. But actually more is true in this case because the bound has a particular relation to this Coulomb branch rank scaling. This comparison's a little bit specious because these operators are R-charged, single-trace, BPS-protected Lorentz scalars. What do they have to do with black hole microstates? Because there are no non-singular BPS black holes with these quantum numbers. But still, the operators fix the central charge, so there seems to be some maybe deeper, more implicit relation between this sector and the black hole sector. In any case, putting the bound somewhere in this plot, it falls between small and large, which is an interesting fact, and in some sense rules out a certain type of pure gravity where you might have hoped or expected to push things up to order C. Yes, thanks for reminding me to do that. There are R scalars below this bound, and R scales like root C, so there are an infinite number of operators below this bound. There's a power law infinity of superconformal primaries below this bound. Yeah. Now, from EFT thinking, you might think that we should define the pure gravity in this context with M Planck, not some higher power of M Planck. Now, the scalars do obey this when C scales like R to the 3/2 or less. This follows from what I said, right? From this. But what about in general, and should they even? Right? So I think we've ruled out a certain kind of pure gravity in this case, but not maybe the purest, although expectations for what that means are muddier than in lower dimensions. Okay. So I'm basically done. Here's a final thought that sort of transposes some of this onto the n equals 4 question. Let's phrase that in a few different ways. First, the traditional way, can the half PPS superconformal primary spectrum be empty above dimension 2, where the stress tensor multiplet sits? Second, with this Regé thinking, can the spectrum of R-charged spin-2 Regé trajectories be empty? And finally, there's a small black hole way to phrase things. Can the non-BPS spectrum start at delta goes like C to the 1/3, which looks like a 5D small black hole, as opposed to C to the 1/8, which is the scaling of a 10D small black hole? Thanks for listening.
Questions?
Since you rephrased the size of the extra dimensions in terms of the Reggie trajectories, you might expect that all these extra Reggie intercepts that you get from the KK tower would show up in Reggie limit or chaos limit of correlators, some subleading Lyapunov exponents or something. Do you know if that shows up in those correlators, or if it's another way of thinking about it?
Yeah, I think, well, the main thing that would happen is that they change the coefficient. So, you look at all the spin-2 contributions, they each contribute like a OP coefficient squared to the 1/Z behavior. And so it would be strictly larger than just the stress tensor piece when you have all these other trajectories contributing. It is hard for me to, so that opens up, I guess, the possibility of addressing the scale separation question by somehow saying that there's a lower bound in this coefficient which is strictly larger than the one coming from just the graviton, but I don't know how to establish that.
Thank you. Can I just ask a very basic question? So how did you know that if such a theory without an S5 existed, why it could not have a weak coupling limit? Can you remind me what was the argument?
Well, so because we're assuming maximal supersymmetry, I'm taking it as given, I think this is true, that there's a unique, so if it has a weakly coupled point, then there's a Lagrangian, and the unique Lagrangian is that of super Yang-Mills. I don't see a way around that statement. I think the closest thing you could expect is somehow that
it was a little bit non-local. Is it so? It's clear that it cannot be smoothly connected to n equals 4. It's
right.
not like we could have n equals 4, deform it a bit, and see the states going away. It's
right.
not possible.
Right.
If it was smoothly connected, would it need to be smoothly connected by a Lagrangian, or could it be smoothly connected by something? Lagrangian clearly implies weak coupling, but is the converse true?
Zero, yeah. So I mean, zero coupling is really what we're referring to, and then we'd have to construct the free theory. So I think yes, we could try to then, split hairs about zero versus weak coupling. You could imagine some theory that somehow the cutoff near the origin is exponentially close or something. Yeah, which maybe is not so crazy, but it's a little bit niche, let's say. I'm not sure if that's really possible. Show that.
For example,
yeah.
Shai was showing that if you use these localization constraints, then the bootstrap is claiming that it was really n equals 4. If you don't, it was something else.
Yeah.
From that point of view, it looks like you could put epsilon after localization and tune epsilon to interpolate.
Yeah. I mean, right. Maybe. Well, but isn't some sort of let's call it evidence against that there was a finite gap between these two bounds they derived? So what if this tuning procedure can't actually correspond to a theory that preserves this n equals 4 superconformal symmetry, else the gap between the one with and without localization would be infinitesimal. Right? So.
What was the role again of this bound by Bonifacio into Bichler for the ratio of successive eigenvalues? You showed this at some point. Why did you need it?
Oh, I didn't need it. It was just for motivation for why you might expect that if there's one massive spin 2, there's an infinite number at the ADS scale. But they prove something mathematical, which is that for this setting, closed Einstein manifolds with no boundary and positive Ricci curvature, the ratio between successive eigenvalues is some order 1 number, and that order 1 number depends on a ratio of eigenvalues of a higher Laplace operator, like the tensor Laplacian. So this plot is a plot of like delta I plus 1, lambda I plus 1 over lambda I, where these are eigenvalues of the scalar Laplacian. That's on the x, and on the y is this other ratio coming from the tensor Laplacian. And it flattens out if this ratio is positive, but it goes up a little bit if it's negative. This order 1 number, so this is an upper bound, the allowed region is below, and if you insist on, so for cases where this ratio from the tensor Laplacian is positive, then this is just 4.
I thought I understood the result. I didn't understand why you cared.
Just motivation.
Motivation for. No, I mean it's a nice result,
yeah.
but in your story,
no, I should care about less. Yeah, I should care about less. That's a good question. It's just funny the way you.
I will rephrase. And, of course, one cares about any results. So
I'm driven into
nice results of this sort, but why? What was the role in your logic?
Because to motivate the idea, which is a little bit apart from what I'm really trying to say, that if n2 is greater than 1, then it's probably infinity. Now, yeah, I mean, it's a very reasonable conjecture, and similar kinds of conjectures have been made that the only two possible values for n2 are 1 and infinity. But
where light means
ADS scale.
Why again? The example was. I will repeat Shiraz's question. Why wasn't that the counterexample?
Because you had lots of operators that were ADS scale, but there was just a sort of micro gap between the lightest one and then the others.
So what you would like to exclude with this logic is the existence of a singular one below and all the others very high.
Yeah, very high.
Yeah,
move the whole thing up a lot.
Okay.
Yeah, rescale it by some delta gap sized number.
Sorry for the stupid question.
Sure.
Hi, thanks. Is this bound still allowing operators that in the CFT would be dual to branes? Because you have delta less equal to the square root of c.
Yeah, good
times
question.
A big number.
So right. So if c scales like n squared, then this is a root n times log correction. Root c is n times log correction, and n is that scale. But these are like just single trace, sort of ordinary operators. So they are not those states So it's in a different sector of the theory. I don't think it would forbid that. Yeah.
I mean, wouldn't you think that you can pile up a lot of branes and eventually pop up some extra dimensions, which you didn't start with, which is large?
I'm not seeing the relation between that comment and the previous one.
Okay, it was just a question.
Sorry, can you rephrase the question?
I mean, if you pile up a lot of branes,
Yeah.
eventually you might pop up an extra dimension, which is large.
Yeah.
It goes as the number of branes you have piled up in the bulk.
Right. I mean, but yeah. I mean, this part of the
and since they are DPS, you can pile up many.
This part of the talk doesn't really have anything. That part of the talk doesn't have anything to say about that scenario. It's just bounding how high you can push the lightest operator. So in the scenario where the lightest operator goes up to root C, then you don't have some large extra dimensions in that kind of theory. But can you have that? Yeah. If everything below is allowed by what I've derived. Yeah.
Thanks.
Sure.
All right. I don't see any other questions. So let's thank Eric again for the talk.